Hi, my name is Bill Kinney. I'm a math professor at Bethel University in St. Paul, Minnesota. It's March of 2020 right now, and that means the world is dealing with the effects of the COVID-19 or coronavirus. And lots of people, teachers and students, are struggling to finish their semesters. High school, college age, younger. I've got a lot of college age resources at my YouTube channel here, Bill Kinney Math, but I've got some high school resources as well, and even middle school resources. A couple months ago, I made a couple practice exam videos for AP Calculus AB. Today, I'm making a sample exam video for AP Calculus BC, which extends the content of AB into things like sequences and series, for example. So I'm going to work through this practice exam. It's section 1, part A. It's no calculator. And you would have 60 minutes to do 30 questions on your test. That would mean 2 minutes per question. Since I'm giving explanations, it's going to take me longer. Some of the problems are short, some are long. In fact, I put one problem in here that's kind of extra difficult. It's going to be number 6. That will take extra long because I want to show you some different ways to do it to confirm that your answer is correct. But let's start with this very first one that you see here. It's a definite integral. And definitely, this integral can be done by guessing. You can guess an antiderivative of this function. This integrand is 1 over square root of 6x plus 1. If you've got enough experience with antiderivatives, you can easily guess that antiderivative. But if you're feeling uncertain, it never hurts to go ahead and do a substitution. In this case, what should the substitution be? Well, sometimes you just have to guess. And the most obvious thing to guess here, is u equals 6x plus 1. Is that a good guess? Well, it certainly will make the integrand function simpler. It'll be 1 over square root of u with a constant multiple in there possibly. And that will be easier to think about what the antiderivative is. What will the constant multiple be? You need to find the derivative of u with respect to x. du dx is 6. You need to pretend this is a fraction and pretend multiplying both sides by dx to get du is 6 dx. Okay. There's no 6 in front of that dx. However, you can divide both sides of this equation by 6 to get 1/6 du is the same as dx. So now go ahead and make your substitutions. dx gets replaced by 1/6 du. That 1/6 also can be brought in front of the integral sign. And you've got a square root of u in the bottom. All right? Now, this is a definite integral problem. The answer is going to be a number, as you can see. And if this is going to be a true equality here, I am not done. I need to have limits of integration here. And when you change the variable here, when you do a substitution, you must change limits of integration as well. Many people don't do that. And it's technically incorrect and it's technically sloppy, and if you're going to get a grade on it, you're not going to get full credit. They end up getting the right answer in the end because they go back to the original variable with the original limits of integration, and they might get the right answer, but would not be full credit. You should practice changing the limits of integration. And there's a bonus if you do change the limits of integration. Not only is it technically correct, but also you never have to go back to the original variable. What would the new limits of integration be? You need to use the substitution equation, u equals 6x plus 1. The original limits of integration are 0 and 4. Just plug those numbers into this equation. When x is 0, plug in x equals 0 here, you get u is 1. So make this a 1. When x is 4, plug in 4 right there, you get 6 times 4 is 24, plus 1 is 25, you get a 25 right here. Okay? Now do this definite integral. You never have to go back to x. I'll go ahead and put the 1/6 out in front. Square root of u in the bottom is the same as u to the negative 1/2. So integrating that, you'd add 1 to the exponent, you get a u to the positive 1/2, you divide by 1/2 as well, which is the same as multiplying by 2. So you get a times 2 u to the positive 1/2, evaluated u going from 1 to 25. 1/6 times 2 is 1/3. You're going to get a 1/3 out in front. Then you're going to have a 25 to the 1/2 minus 1 to the 1/2. That's a 5 minus 1, or 4. 4 times 1/3 is 4/3. The answer is A. Right there. Okay? That is the correct answer. Let's move on to number 2. So you look this over, you see that it's an improper integral. think I'm going to switch to red here. An improper integral. Technically speaking, improper integrals may not exist. They may diverge. Hopefully you know that when you have an exponential decay, it does converge. And technically speaking, by definition, it's really a limit. It's a limit as the upper limit of integration, if you call it b, goes to infinity, if this limit exists. Now, truth be told, you can be sloppy here too and not put the limit sign and still get the right answer even if you're not being careful. But I do want to recommend being careful. So I'm going to go ahead and put the limit sign there. This is the definition of what this improper integral is. It's improper because of the infinity sign there. Another way an integral can be improper is if you've got a vertical asymptote at the left or right endpoint of integration. All right? Technically, it's a limit, though. Just carry the limit sign along, and only let b go to infinity at the end. What's an antiderivative of e to the negative 2x? You can do a substitution again. You could do u equals negative 2x, and so du would be negative 2 dx, because du dx would be negative 2, and then we'd pretend multiplying both sides by dx. And you technically need to change limits of integration again. This time I'm actually not going to change limits of integration, and it is okay as long as I go ahead and write down your antiderivative of this right away. It can be found by guessing. Negative 1/2 e to the negative 2x. Okay, that antiderivative can be found by guessing. And you then can keep your original limits of integration. With the other problem, it might have been a little harder to guess, and definitely in some substitution problems, it's really hard to guess. But here it's fairly easy to guess if you've got some practice. Okay? So now go ahead and plug in your limits of integration. You always have to be careful about minus signs in this kind of thing. There's a minus sign here. We have negative 1/2 e to the negative 2b when we plug in x equals b. Then we need to subtract, because I'm using the fundamental theorem of calculus, what I get when I plug in the lower limit, 0. Negative 1/2 e to the negative 2 times 0 is e to the 0. Does the limit of this as b goes to infinity exist? Yes, because that term right there with the exponential decay definitely goes to 0 as b goes to infinity. Sometimes you might have a b or a b squared in front of it, and you might be wondering, if I multiply this by b or b squared, does it still go to 0? The answer would be yes when you've got this exponential decay there. Proof of that would require L'Hopital's rule, though you really wouldn't have time for that on the exam. You would just need that knowledge. If you multiply this by b to the n for any positive value of n, you're going to get something that goes to 0 as b goes to infinity, and even negative values of n as well. So this goes to 0, and the two minus signs cancel here, giving you plus 1/2 e to the 0, but e to the 0 is 1. The answer is 1/2, and that is choice C. Okay? Would be a good idea, if you're really trying to get the much as you can out of this video, is to try these problems before I do them, okay? So you can pause the video as we go. Number 3. The position vector of a particle moving in the xy plane at time t is given by that formula there. What is the speed of the particle at time t equals 1? Okay? So you've got to know your facts here. This defines a parametric curve, some curve in the plane. I'm not going to try drawing it. You could trace out that curve as time goes by in parametric mode in your calculator. You could draw a position vector from the origin to the spot that the curve is at time t and see that arrow change as time goes by. What is the speed? It's not the same as velocity, though it's related. The velocity here is a vector, and you typically draw the vector so that it's based at the location of the object as it moves, and then it would point in the direction tangent to the curve of motion. That's the velocity, it's a vector. The speed is the length of the velocity vector. It's a scalar, a number. Okay, and you can see the answers are numbers. So we've got to find the velocity vector first, and then we need to find its length or magnitude. How do you do that? It is the most logical thing you could think of here. You just differentiate these components one by one and keep the I and j as they are. And often I call those I hat and j hat because that's the way I learned it in my physics classes. Keep those as they are. They're called unit vectors, standard unit vectors, and they help you think about the vector geometrically. I'm not going to make drawings here. I'm just going to tell you what to do. So take the derivative of 5t squared minus 4t. You'll get 10t minus 4. It's supposed to be a minus sign there. 10t minus 4. Keep the I there. You can write it as an I. I like writing it as an I hat. Plus, take the derivative of this thing, negative 2t plus 3. Keep the j as it is. You can write it as a j, but I like writing it as j hat. That's just me. That's many physics teachers do that. What then is the speed? Both, by the way, these things are functions of t. I can put of t's in here. What is the speed? It's the length of the velocity vector. And if you draw it, you can make a right triangle, and you can use the Pythagorean theorem to figure out its length. And it turns out to be the square root of this first component squared, 10t minus 4 squared, plus the second component squared, negative 2t plus 3 squared. That's the speed in arbitrary time t. Now plug in t equals 1. You don't need to expand it out. In fact, I could have plugged in t equals 1 into the velocity vector right away and found the length of the velocity vector right away. But it's worth emphasizing the speed really is a function of time. It's not constant. Go ahead and plug in t equals 1 here. The speed at time 1 would be the square root. 10 minus 4 is 6. You'd have a 6 squared. And then a negative 2 plus 3 is 1. You'd have a 1 squared. Square root of 36 plus 1 is square root of 37. That would be the answer. Choice C. Okay, and its units would be in units of distance per unit of time, and that is a scalar. It's a number. The velocity is a vector. On to number 4. Oh, kind of a nasty looking limit problem. Can't plug in 4, right? You'd be dividing by 0. This is where you hope you can use L'Hopital's rule. And yes, you can, but it really should be checked first. You need to check that this is really a 0 over 0 indeterminate form. Are both the top and the bottom going to 0 as x approaches 4? Certainly the bottom is. 4 minus x is approaching 0 as x approaches 4. What about the natural log of x minus 1 over 3? Well, by continuity of the natural log function, you can take the limit inside first. As x approaches 4, the fraction inside is approaching 4 minus 1 over 3. 3 over 3 is 1. And the natural log of 1 is 0. Yes, this is a 0 over 0 indeterminate form. And that really should always be checked. And it's within the realm of possibility that they could be making the problem extra tricky and be a problem where you can just evaluate the limit right away by substitution. And you get the right answer. And if you use L'Hopital's rule, you would get the wrong answer. So you really should double check that it's 0 over 0 or infinity over infinity. In this case, it's 0 over 0. Before we use L'Hopital's rule, I'm going to use a property of logarithms that's going to make differentiating a little bit easier, a little bit less likely to make a mistake. The natural log of a quotient of a fraction is the difference of the log at the top minus the log at the bottom. We've got natural log of x minus 1 minus natural log of 3. That might make it also more clear that the top goes to 0 as x approaches 4. Right? That makes differentiating the top a little easier. You'd be a little less prone to make a mistake. Now I'm going to apply L'Hopital's rule. And what does L'Hopital's rule say? It says the limit of this 0 over 0 indeterminate form will equal the limit of a new ratio that is not found by the quotient rule. Don't ever think you're using the quotient rule here. You've got to differentiate the top and the bottom individually and make a new fraction. The derivative of the top, well, that's a constant. It differentiates to 0. The derivative of natural log of x minus 1 is 1 over x minus 1 times 1 if you're thinking in chain rule. The derivative of x minus 1 is 1, but of course I don't have to write times 1. And the derivative of the bottom with respect to x is just a negative 1. Now, this fraction is not an indeterminate form. I can go ahead and plug in x equals 4 right away and get a 1/3 on top divided by negative 1. The answer is negative 1/3. And that is choice A. Okay? That's problem number 4. Number 5. This one's kind of confusing. We've got a function, really, defined by an integral. Y equals, there's no f of x in here, but you could certainly write f of x if you like. And maybe you'd even prefer writing it as capital F of x, because it is an integral where the upper limit of the integral is the variable. This is a situation where when you see it, alarm bells should go off in your head saying, I need the second fundamental theorem of calculus, probably. Or that might make it easier, at least. That's my function that's going to have a graph, and I want to find the length of that graph between x equals 0 and x equals 12. Okay? Not the length of that function, the length of capital F. Need the formula for the arc length. Over some interval. In this case, it's 0 to 12, but in general, it would be a to b. This is something you should memorize. It's the square root of 1 plus the derivative of the function. I'm going to write the function as capital F here again. Squared. Capital function, f is a function of x. I'll go ahead and call it an x here. dx. So that's the thing that I ultimately have to calculate. So if I'm going to calculate it, I need f prime. That's where the second fundamental theorem of calculus comes in. Second FTC implies that the derivative of capital F is this integrand. But if you're calling the variable x here, you should call it x over here. Okay? Be consistent in your variable there. The u there is just called the dummy variable. It doesn't really have any meaning. I could have used w, I could have used t. It doesn't matter. X is the variable for the function I'm interested in. This can be simplified, if you like, to square root of x over square root of 4. Square root of 4 is 2, so this is 1/2 square root of x. Although I guess I didn't have to do that because I'm going to square it. So the integral that we need to do is the integral from 0 to 12 of square root of this thing squared, which just really makes the square root go away. You get an x over 4. This is somewhat similar to the very first question now. We can do this integral by substitution. U equals 1 plus x over 4. Du would be 1/4 dx. So du would be 1/4 dx. So dx would be replaced by 4 du. So let's change color here. I get a 4 that I can bring out in front. I have a square root of u, that's u to the positive 1/2 power. Got a du, and again I need to change my limits of integration. Don't be sloppy here. Go ahead and make the change. When x is 0, u is, use this equation here, u is 1. When x is 12, 12 over 4 is 3, plus 1 is 4, u is 4. This is the integral to finish the problem. You get u to the 3/2 divided by 3/2, which is the same as multiplying by 2/3, and now my pen's is failing me here. Dividing by 3/2 is the same as multiplying by 2/3. U to the 3/2, u goes from 1 to 4. This is 8/3 here, 8/3. 4 to the 3 halves is 8 because it's square root of 4, 2 cubed, which is 8. 1 to the 3 halves is 1. 8 times 7 is 56. You get 56 over 3. That is answer B. That's the final answer right there. Okay? That would be the length of this function. You don't have to bother graphing it, and you can't because you don't have your calculator. But you could try to estimate it. It's not worth taking the time to do that. All right, here we are to the problem I made kind of extra difficult. And I'm sure this is going to take me extra long here now in making this video to go through this problem because I'd like to do it really in 3 ways. Okay? The first way I'm going to do it is, at least for this problem, the way I'd recommend doing it that's going to get you to the answer perhaps most quickly. Well, maybe, maybe not. It would be, I think, the simplest way to think about it, especially if you don't remember formulas for the second derivative of y with respect to x when you've got parametric equations. If you don't remember that formula, at least for this problem, you'd have to do it in the way I'm about to show you. X equals cos squared t, y equals sine t. That's going to mean, what I'd like to do is I'd like to figure out how y depends on x here, okay? And then just take the second derivative in the ordinary way. Though I'd have to figure out what x is when t is pi over 3 to finish the problem. So how do I relate x and y? X is cos squared t. How do I relate that to the sine? Use the standard, very famous Pythagorean identity, cos squared t plus sine squared t equals 1. Therefore, cos squared t equals 1 minus sine squared t for all t. That's an identity. It's true for all t. But sine t is y. So this is 1 minus y squared. So no matter what t is, the point on the parametric curve defined by these parametric equations would be on, satisfy the condition x equals 1 minus y squared, which you can now solve for y as a function of x. Y squared would be 1 minus x, and that means y would be plus or minus square root of 1 minus x. When t is between 0 and pi over 3, both the sine function is going to be positive here. I can take the positive square root. Square root of 1 minus x, or 1 minus x to the 1/2 power. I'm going to call that f of x. So now my problem is to find f double prime of x, plug in whatever x is when t is pi over 3. I'd have to plug t equals pi over 3 into here to figure out x, but let's take the derivatives first. This is a 1 minus x quantity squared. Maybe if I hold the eraser, it won't fail me as much. No, maybe not. Differentiate that, bring down the 1/2. Subtract 1 from the exponent. Chain rule, multiplied by the derivative of 1 minus x is -1. So this is -1/2, 1 minus x to the -1/2 power. The second derivative is going to bring down the -1/2 there. -1/2 times -1/2 is positive 1/4. 1 minus x, -1/2 minus 1 is -3/2. You get another -1 because of the chain rule again. I have to plug in x into that. But what is x? When t is pi over 3. X is cos squared t, so I'm going to get cos squared pi over 3. Do you need to memorize some trig values for the test? Cosine of pi over 3. Well, pi over 3 is 60 degrees. Okay, I remember cosine of 0 is 1, then I go down to square root of 3 over 2, then square root of 2 over 2, then 1/2. Cosine of pi over 3 is 1/2. So I got to do 1/2 squared, and get 1/4 here. Now plug that into f double prime to get the answer. F double prime of 1/4 will be -1 over 4. 1 minus 1/4 is 3/4. I'd have, I guess I have it to the positive 3/2 power if I'm putting in the denominator. 3/4 to the positive 3/2 power. Let's see. 4 to the 3/2 is again 8. 3 to the 3/2 I could write as 3 square root of 3. 4 and the 8 cancel to give me 2 down there, which I could think of as a 2 up here. Negative 2 over 3 root 3. Oh, pen is failing. Rationalizing the denominator to try to get it into one of these forms, I'd want to multiply the top and the bottom of this by square root of 3. If I do so, I get negative 2 square root of 3. 3 root 3 divided times square root of 3 is 9. The answer is D. Take a breath. Let's do it a couple other ways. Partially to save some time and partially because I kept making mistakes, I'm going to give you the second solution pre-written out. I did this like 3 or 4 times and I kept making a mistake every time. First of all, it involves a formula you would never guess unless you had it memorized. The second derivative of y with respect to x in terms of derivatives of x and y with respect to t is this. It's not y double prime divided by x double prime, unfortunately. It's this crazy thing. And with this particular problem, if you use this, it's just so easy to make mistakes. And again, I kept making mistakes over and over. But I went ahead and I took those derivatives, like for example, this thing here, negative 2 cos t sine t, is the derivative of x with respect to t. Think about that. That's the chain rule involved. This is y double prime. Here's y. Y is sine t, so its second derivative would be negative sine t. Minus this minus sign is that minus sign there. This is x double prime. This is y prime. Certainly y prime is fairly easy. To get this, you need to differentiate this thing with the product rule. I'll leave it to you to double check that this thing with the minus sign there differentiates to this. And then, stop it. Then, there we go. Then, divide by x prime cubed. I've got to take this thing there and cube it with the minus sign there. It cubes to this, involving a negative 8 in front. Now plug in t equals pi over 3 using these facts here that cos pi over 3 is 1/2, sine pi over 3 is square root of 3 over 2. Plug those numbers in. For example, you get a cos t, that's the 1/2 here. You get a sine squared t, and by the way, the 2 minus signs canceled here to give a plus. Square that, you get 3/4. Minus 2 sine squared is that. Minus 2 cos squared is 1/4. Cos t is 1/2. Then on the bottom, I got negative 8 times this thing cubed is 1/8 times sine cubed. Cube this thing, you get 3 root 3 over 8. Then you simplify, you do get the same answer as before. 2 root 3, negative 2 root 3 over 9, which is choice D. I'm going to stop the video again so that I can do the third way efficiently as well and not make mistakes. And now I'm back with the results of the third method, which involve using this formula right here. Take the derivative with respect to t of the ratio y prime of t divided by x prime of t, which is really dy dx, all divided by x prime of t. This, by the way, can be derived with the chain rule. If you do all the details of this, you see that it really ends up doing the same final calculations as the preceding method. Okay, that's where the preceding method's formula comes from, really. Do notice that here, for example, I need to use the quotient rule when I differentiate that to get this big fraction here up top, and then I still have this negative 2, so there should be a negative sign, negative 2 cos t sine t on the bottom, and that carries down that right there. And then I can combine the fractions into one, essentially, by combining these two as part of the new denominator and plug the numbers in for t using these values again. And once again, you get the same final calculations and the same final answer. Yay. Wow, that took me a long time. I know it was a long time to watch as well, but I hope it was worth it in terms of just realizing that you can do things different ways. And technically speaking, you know, if you want to do this in general, you do need to memorize one of these last two formulas. But hopefully your problem wouldn't be quite so nasty in terms of how easy it would be to make mistakes. All right. All the rest of the problems are not quite as long as that, and some of them are very quick. So hang with me here. All right, here we're back to an improper integral. 0 to infinity of 4x cubed divided by 1 plus x to the 4th squared. Now before you actually do any calculations here, you should think about it and realize that this is a 3rd degree polynomial divided by really an 8th degree polynomial. It's a rational function where the degree of the top is 3 and the degree of the bottom is 8. The degree of the bottom is more than 1 more the top. And in that case, these kinds of improper integrals do converge. Non-existent is not the correct answer right away. Okay, it's going to be either B, C, or D. You can do a substitution to help you do the integral. U equals 1 plus x to the fourth. That's really nice. It's set up so that du is sitting there right for you. It's 4x cubed dx. Okay? Because du dx would be 4x cubed. Again, you could get away without writing limit signs, but just to emphasize its importance in terms of the definition of improper integrals and to avoid some mistakes that could occur with harder problems, I'm going to go ahead and put the limit sign in there. Really what I've got then is du over u squared. It's u to the negative 2. du. If I'm changing limits of integration, even in here with this limit in here, I do need to change the limits of integration. When x is 0, u is 1, not 0. When x is infinity, or you could replace it with infinity if you didn't have a limit sign, but when x is b, replace x with b here, you're going to get 1 plus b to the fourth. That's okay. That's the upper limit of the integral when you change the new limits of integration to the new variable. Now take this limit, you're going to add 1 to the exponent to get a negative 1, and divide by negative 1, which is the same as multiplying by negative 1. Careful with negative signs. You're going to really have negative 1 over 1 plus b to the fourth minus negative 1 over 1, or just negative 1. This thing does go to 0 as b goes to infinity. The answer is 1. That is choice D for number 7. Okay? Again, technically you're just after right answers here. But if you do things in the technically correct way, it can help avoid mistakes. And it really is beneficial for future math classes where you might need this stuff and you don't want to make mistakes. I'm thinking in particular of multivariable calculus where you need to do double and triple integrals in like what are called polar and spherical coordinates, and you have to change your limits of integration on those or else you're definitely going to get it wrong. All right, this one looks really hard at first. It's not nearly as hard as it looks, though it is still tricky. How do you do it? Well, we're fortunate here in the fact that the thing under the square root is a perfect square. Think about it. If you think about factoring it, it is x minus 3 quantity squared. And then you look at that and you might be jumping for joy. Square root of a square, I can get rid of the square root in the square. I can integrate x minus 3. No, not so fast. The square root of the square of a number is not equal to the number. It's equal to the absolute value of the number. Which, of course, does equal the number when the number is greater than or equal to 0. But if the number is negative, they're not equal. So I really should think of this in terms of the absolute value of x minus 3. Which tells you, and this can make sense even thinking about the original function in its original form, the answer can't be negative. We're integrating a function that's greater than or equal to 0. B and C are ruled out right away. It's got to be either A or D. Now you could do this integral by drawing the graph of this absolute value of x minus 3. It's the absolute value function shifted to the right by 3. We're integrating from 0 to 3, and the value here would be 3. The answer is the area of this triangle. 1/2 base times height is 1/2 times 3 is 9/2. 9/2 is the answer. But you should feel comfortable thinking about it another way. When x is between 0 and 3, x minus 3 is negative. Its absolute value, therefore, is its opposite, negative of, in parentheses, x minus 3, which would really be 3 minus x. in general, the absolute value of a number is the square root of its square, but it also can be written piecewise as a itself if a is greater than or equal to 0, and the opposite of a if a is less than 0. Now this is confusing to many people. Don't let it confuse you. The opposite of a number is not necessarily negative. The negative of a number is not negative. It's not necessarily negative. In fact, the negative of the negative is positive. And taking the opposite of x minus 3, this 3 minus x is negative of x minus 3, and is a positive quantity when x is less than 3. We do get a positive answer here. I do this integral with the fundamental theorem. When I plug in 0, I'll get 0. When I plug in 3, I'll get 9 minus 9 halves, which is 9 halves. Positive 9 halves is the answer. So it's not a difficult problem when you see the trick at the start, but you need to not get tripped up by the next trick, the fact that you need to think about this fact there, use absolute value signs, and either think about a graph or switch this around because x happens to be less than 3. If x were bigger than 3, then you'd replace this with x minus 3 itself. Which of the following statements is true? Got some series here. By the way, I do want to tell you right now, as this problem comes up here, that I have more series examples on my sample practice exam than you probably get in a real calculus BC exam. I wanted to emphasize the series, partially because it's not in my AB video. A lot of what we do in BC is the same as AB. It's just some extra stuff that comes up in BC. So because this topic is not on my AB video at all, I wanted to put some more of it in BC. All right, which of the following statements is true? More than one could be true. This sum is absolutely convergent. This sum is conditionally convergent. This sum is conditionally convergent. You need to know, of course, then know what absolutely convergent and conditionally convergent mean. And you also need to know some basic facts about series. Okay, you can't do this kind of stuff without factual knowledge. What does it mean if this was absolutely convergent? It would mean that if you sum up the absolute values of the terms, you still get a convergent series. Is that true? Well, the absolute value of those terms that you're summing just gets rid of that negative 1 to the n plus 1 power and replaces it with a positive 1. And what you have here is called a p-series, with p, the coefficient of the n in the denominator there, equal to 2. And this is factual knowledge you should have. For p-series, you're going to get convergence when p is bigger than 1. 2 is bigger than 1, so we will get convergence. Okay? And that means, because this series converges, that this series converges absolutely. The corresponding series where the terms that you're adding are the absolute values of the original terms converges. Therefore, this one converges absolutely. You might question, you might wonder, does that mean it actually converges? Yes, absolute convergence implies convergence. This thing definitely converges as well. That can also be proved with something called the alternating series test. Which is relevant for number 2. Is this series conditionally convergent? It's going to be conditionally convergent if it does converge, but the corresponding series whose terms are the absolute values of these terms does not converge. This does converge by the alternating series test. This is an alternating series. The terms are -1, then +1/2, then -1/3. They are alternating in sign. And moreover, their absolute values are going towards 0. By something called the alternating series test, this series does converge. However, the corresponding series of absolute values of the terms is called the harmonic series, and that diverges. It's also a p-series with p equal to 1. And when p is 1, it diverges. If p is bigger than 1, then it converges, just like in part 1. It diverges if p is less than or equal to 1. But this has a special name, even again, it's called the harmonic series. It diverges. Therefore, this series is conditionally convergent. So 1 and 2 are both true. Is 3 true? Does this converge by the alternating series test? No, it doesn't. These things do not approach 0. And in fact, that's enough to say right away the series doesn't converge at all. The terms overall do not approach 0. This n plus 4 over n plus 3 approaches 1 as n goes to infinity, and the terms, in fact, that you are looking at with this negative 1 to the n there alternate between numbers that are close to 1 and close to negative 1 when n is large. Such a series diverges by something called the divergence test. So it doesn't converge at all. In particular, it also doesn't converge conditionally. So the answer is 1 and 2 are true. B is the answer here, 1 and 2 only. Okay? I think I should summarize that again real quick. Is this series absolutely convergent? It does converge by the alternating series test. Also, because the corresponding series whose terms are the absolute values of the original series converges by something called the p-series test, or because it's a p-series, that's enough to say this converges absolutely, and absolute convergence does imply convergence. You know, it's all confusing. You really understand your concepts carefully. Is this conditionally convergent? First of all, it has to converge. Yes, it converges. The terms alternate in sign, and they approach 0 monotonically, actually is important as well. If their absolute values do. And therefore, this converges. But the corresponding series, whose terms are the absolute values of the original ones, is the harmonic series, which we know diverges. Therefore, we say this conditionally converges. Finally, this one doesn't converge at all, so it doesn't converge conditionally. The terms don't go to 0 even, but the divergence test, that's enough to say this series diverges. So 1 and 2, again, are the only true statements here. We're 1/3 of the way through. If you've stuck with me through this whole thing so far, that's pretty impressive. But maybe you're just doing one problem at a time. That's fine too. Number 10. It's not as hard as it might look at first, though you do need to think clearly about concepts. We've got a solid that's formed by taking a region in the first quadrant and in a third dimension creating a solid whose cross-sections have a certain shape. So the region that we start with is in the first quadrant. It's bounded by the curve y equals square root of cos x between 0 and pi over 2. Looks somewhat similar to the cosine graph, except it sort of stays higher longer before going down to 0. This is the region that is going to be the base of our three-dimensional solid. So now I'm making a drawing that you want to imagine as a three-dimensional drawing. There's the x-axis here, the y-axis here. This is an xy plane, so to speak, going into the screen. And then there's a third, say, z-axis up here for a third dimension, going straight up. This region in the plane, I can redraw with some perspective kind of about like that. And then I want to think about the solid. Each cross-section of the solid perpendicular to the x-axis. Cross-section means a cut. Take a knife, take your hand, pretend it's a knife, and cut it perpendicular to the x-axis. So my hand here is perpendicular to the x-axis. Is a square. The base of each square for any given value of x would be a line like this. The square itself then would look about like that. And when x gets close to pi over 2, the square is going to get smaller because the base is smaller. Technically, at pi over 2, it's just a point instead of an entire square. It's biggest when x is 0. So you can draw a bunch of these things to sort of get a feel for what your solid looks like, if you like. Though you can do the problem without making a drawing, although I think it's probably helpful. For any given value of x, what we want to do is we want to find the area of this cross-section in terms of x. And then that's the function you integrate to find the volume of the solid. You can argue in terms of Riemann sums or infinitesimals if you like to verify that, but that's what you do. The integral from 0 to pi over 2 of the cross-sectional area function is going to be the volume that we want. This is the cross-sectional area function. Cross-sectional area function. In this case, it's kind of nice because the cross-sectional area function can be found fairly simply as just doing base times height, or the base of a square squared. For any given x, the base of the square is this distance there, which comes from this graph, which is y equals square root of cos x. So that's the thing I've got to square. A of x is the square root of cos x quantity squared. And cos x is positive for x between 0 and pi over 2, or at least non-negative. The square root does exist as a real number. You square it, you will get cosine of x. I mean, you could put absolute value signs around that, but you don't have to. Okay, and that's not the point here. The point in that other problem was the square root of a square is the absolute value of the number, but that's not what's going on here. This cosine of x is greater than or equal to 0 anyway. We're not dealing with any imaginary numbers here. Anyway, that's the function you integrate. It's a fairly simple integral. You get sine x evaluated from 0 to pi over 2. Sine of pi over 2 is 1. Sine of 0 is 0. And the answer is 1. Shall I say? Okay. Problem can be made more difficult. Like if your cross-sections are semicircles, then pi would become involved. Or if they were equilateral triangles, then square roots would become involved because of the Pythagorean theorem. It can be made more complicated. I would encourage you to even try some examples like that on your own. On to number 11. This one's a bit of a pain. Pretty easy to make a mistake on, kind of like number 6. So hopefully I won't make a mistake this time. Try to do it right away without making a mistake. It's a differential equations problem. How do you know that? The number of cells of a certain type of bacteria increases continuously at a rate, there's your key word, rate, derivative, equal to the 3 more than 4 times the number of bacteria present. Wow. If there are 10 bacteria present at the start at time 0 and 53 present t hours later, what is the value of t? Yeah, it sounds hard. And yeah, the calculations are not super pleasant. Pretty easy to make a mistake. But let's write it as a differential equation. First, if y represents the population, dy dt is the rate of change of the population, and the assumption here is that it's a continuous increase, so we can use differential equations. 3 more than 4 times the number of bacteria present. 4y is 4 times the number of bacteria present at any moment in time. And we want to go 3 more than that. So there's your differential equation. Okay? That's the first hard step, is realizing that's your differential equation. We also have an initial condition that y of 0 would be 10. I'll use that later. Let's solve this differential equation. How? Separate variables. You want all the y's on the left, say, and all the t's on the right. Pretend that you're multiplying both sides by dt, even though that's not technically what's going on. Divide both sides by 4y plus 3. You can write the differential equation in this differential form, it's sometimes called. And when you have it in this differential form, you want to then integrate both sides. The left side can be done with a substitution. The right side can be done very easily as just t plus an arbitrary constant. I'm going to call this arbitrary constant C1 instead of C, because there's going to be a C2 and a C3 perhaps, and a C4 perhaps before I get my final C, just to keep those distinguished from each other. Integral, well, the left side, again, could be done with substitution, or could just be done by guessing. If you guess, you'll get 1/4 natural log of the absolute value of 4y plus 3 plus c, but then that c can be subtracted from both sides, and you can write this then as t plus, say, c2, where c2 is c1 minus the constant you get from the left side. What's the goal here now? Solve for y. That's the goal. I want to isolate y on the left side, say. So it'd be nice to multiply both sides by 4 first. Can I get rid of the absolute value signs? That'd be nice. Turns out you can. I'm not going to completely justify that other than saying y is positive. So I'm going to go ahead and get rid of the absolute value signs. You do need to multiply the 4 by t, but you don't really have to multiply the c by 4, excuse me, especially if you call it c3, say. Some people are real sloppy in all this. They put c's all along the whole way, and they still get the right answer. Okay, it's one of those things again. But I'll go ahead and be a little extra careful here and write c1, c2, c3, etc. Now I want to solve for y, get rid of the natural log, exponentiate. E to the natural log of 4y plus 3 would be just 4y plus 3. E to this thing would be e to the 4t times e to the c3, which I could write as c4 e to the 4t, where c4 would be e to the c3, e to the c3, excuse me. Getting confused here. Which is technically positive, so I should have maybe got rid of my absolute values at this step, but don't worry about it. Now subtract 3 from both sides. 4y will equal c4 e to the 4t minus 3. Then divide both sides by 4, and now I'll just call it, instead of c5, I'll just call it c. Okay, there's a function that should be a general solution of this differential equation here. And if you check it, it is. Its derivative would be 4c e to the 4t. That would be what the left side simplifies to when you plug it in. If you plug it in the right side, you get 4c, and which you would now want to write it as a different c, times this minus 12, and then plus 3. Oh boy, did I make a mistake? Let me just double check this here. I could have made a mistake. Hang with me here. Oh, yeah, if my mistake is at the very end, I should divide this by 4. There should be a 3/4 here. Yeah, then when you multiply by 4, you'll get, from here, you'll get the 4 is canceling, giving you a minus 3, which cancels with the plus 3. It does work. That's the mistake. Good that it's at the very end. Now, use the initial condition. I'll go to green now. Or maybe I should do black. 10 bacteria are present at time 0. Y of 0 is 10. Thinking of y as both a function name and as variable here, don't worry about that. Plug in t equals 0. E to the 0 is 1. You get c minus 3/4. So c is 10 plus 3/4 would be 43/4. And plugging that in for c would give you what's called the unique solution of the differential equation. But to finish the problem, we want to solve for t based on there being 53 bacteria at a certain time, and that's no good there. Let's go over here. 53 bacteria present at time t. It's going to be 43/4 c e to the 4t. The goal here is to solve for t. So I now want to add 3/4 to both sides. 43/4 c e to the 4t. 53 is the same as 212 over 4. Plus 3 over 4 is 215 over 4. The 4s would cancel. The C is 43/4. E to the 4t is going to be 215 over 43, which amazingly simplifies to a nice number. That is 5. Now take the log of both sides. 4t will be natural log of 5. T is going to be 1/4 natural log of 5. Choice B. Okay, so yeah, that one's a nasty one. This one looks pretty nasty. One of those integrals where the variable is in the upper limit of the integral. It's not as hard as it looks. We can solve this one pretty quickly. It's not as hard as it looks. G is this function. It's this function defined by an integral where the upper limit is the variable of this function, little f. Again, alarm bells should go off in your head. That means by the second fundamental theorem of calculus, second FTC, that the derivative of g at an arbitrary value of x equals little f at that same value of x. There's an x there, not a t. And this is true for all x in this interval between -2 and 4. What are we after here? We're after the maximum value of g on this closed interval. This is the graph of f, not g. But by what we've just figured out, this is the derivative of g. It's telling you the slopes of g. Graph of f here. So when this graph is positive, for example, g is increasing. And when this graph is negative, g is decreasing. So the graph of g has got to be going up when x is between -2 and 2, and start going back down when x is bigger than 2. It's got to have a maximum at 2. So as long as I can find g of 2, then I'm done. But that can be found with the formula for g. We need to integrate this function over here from -1 to 2. And you don't need the formula for the function. Just think about areas. And by the way, if you want to label this axis with anything based on this symbolism, it'd probably be best to label it with a t. So, okay. So we need to just find that integral, which we can do by finding the area of this trapezoid and adding on the area of this triangle. The area of a trapezoid is the average, the base times the average of the two heights. The heights are 1 and 2. The base is 1. The average of the heights is 1 plus 2 over 2. And the triangle has area 1/2 base times height. So we get 3/2 plus 2 is 7/2. That's the answer, choice B. Okay, so if you know your content well, you can do it pretty quickly. All right, this one's a Taylor polynomial problem, as you can see. We're after which one of these is the Taylor polynomial for the natural log function about x equals 1. So they all have x minus 1s to powers in them, which is good. That means they're all in the right form, although if one of them wasn't in the right form, that would allow you to rule it out right away, assuming they're not trying to trick you and say it's equal to that anyway. Also notice that once we get to the third degree, we could actually stop because all those coefficients are different. We don't really have to go to the fourth degree, though I will anyway. We need the derivatives of this function out through the fourth derivative. Derivative of natural log of x is 1 over x, which x to the -1. Second derivative is then negative x to the -2. Third derivative is positive 2x to the -3. And fourth derivative is negative 6x to the -4. So I'm assuming you know to do this for Taylor series right off the bat here. We need to plug in the 1 here. F of 1 is natural log of 1 is 0. F prime of 1 is 1 over 1 is 1. F double prime of 1, plug in 1 here, you get -1. F triple prime of 1, plug in 1 here, you get 2. And F quadruple prime of 1, you plug in 1 right there, you get -6. Right? Then the formula for the Taylor series would be f of 1 plus, divided by 0 factorial if you like, plus f prime of 1 divided by 1 factorial times x minus 1 plus f double prime of 1 divided by 2 factorial times x minus 1 squared plus f triple prime of 1 divided by 3 factorial times x minus 1 cubed. Finally, plus f quadruple prime of 1 divided by 4 factorial times x minus 1 to the 4th power. Plugging in the numbers, that one's 0, f prime of 1 is 1, so you get 1 times x minus 1. Sorry. F double prime of 1 is negative 1, so we get minus 1 over 2 factorial is minus 1/2 x minus 1 squared. F triple prime is positive 2. Positive 2 divided by 6 is positive 1/3. And at this point, we actually could stop and say our answer is choice A. Let's just confirm the last one. F quadruple prime of 1 is negative 6. Negative 6 divided by 24, 4 factorial, sorry about the pen here, is negative 1/4. So that's consistent with answer A. Okay? More series, radius of convergence. There's a couple different ways of finding the radius of convergence. Well, maybe more than 2 ways. It depends on the nature of the series. For certain special series, you can just memorize it based on knowing that it's a geometric series, for example, or a series that's a Taylor series for some function, if it's simple enough. This is complicated enough that it looks like that probably wouldn't work. Even so, there's a couple ways to find it. If you call this thing here AN, what you can do to find this radius of convergence for this series, this power series, is calculate the limit as n goes to infinity. The better way to write it in general is the absolute value of an plus 1 divided by the absolute value of an. And then whatever you get, you can take its reciprocal at the end. And if you get a 0, the reciprocal is thought of as infinity. So the answer can be infinity in general, though it won't be in this problem. You also could take the limit of the reciprocal of this, and that is the answer. And if you get infinity, the radius would be infinity. Yet a third way, I guess there's 3 ways, is to consider the entire expression, including the x minus 4 to the n as being the an, and taking the limit of this thing as n goes to infinity, and saying, by the ratio test for convergence, I want that limit to be less than 1. Now, that's a lot to take in just a minute there. The way I learned back when I was your age was doing it this way and then taking the reciprocal of the answer. I don't have the time to justify the other ways of thinking about it, especially the one that involves x minus 4 to the nth power. Anyway, if you replace n with n plus 1 here, let me just go ahead and write it as a fraction. You get an n plus 2. If you replace that n with n plus 1, and you replace this n with n plus 1, you get 2 times n plus 1 is 2n plus 2, plus another one is 2n plus 3. And I might as well have that 3 to the n being the same fraction, except replacing n with n plus 1. So that is the absolute value of an plus 1. I don't need the absolute value signs, because I've got positive quantities here, which is a nice way to not worry about the x there. Then divide by an, which is the same as multiplying by the reciprocal of an. So I will get 2n plus 1 times 3 to the n divided by n plus 1. Then you get some cancellation. The 3 to the n cancels with almost all of those to leave you with a 3 there. And what's left over now is the limit of a rational function where the degree of the top and the bottom are the same. They both have degree 2. And therefore, the limit will exist and equal the ratio of the coefficients of the highest powers. Highest powers on the top and the bottom are n squared. What's the ratio of their coefficients? The top one, n squared term, would have a coefficient of 2, coming from n times 2n squared. The bottom one's going to have a coefficient of 6. You've got 2n times n gives you 2n squared, times 3 is 6n squared. So this limit can be found to be 2/6 or 1/3. Okay? You could expand it all out, use L'Hopital's rule, but you don't need to. It's going to save time if you just know that fact. Take the reciprocal of that, the answer is going to be C. It's going to be 3 for the radius of convergence on this problem, and I'm just double checking my answer at the moment. For 14, C, yes. Okay? The interval of convergence then, the radius of convergence being centered at 4 is going to go from 1 to 7, maybe including the endpoints, maybe not. And in fact, I think my next problem involves an interval of convergence. Yes, you're given now that the radius of convergence of the series in this problem is 1. What is the interval of convergence? This is a power series centered at 3. 3 here. Its radius of convergence is 1. Thinking of this as being a radius equal to 1. It's not a circle, at least not in the not on the real axis. If you extend this to what's called the complex plane, then it can become a circle or a disk and a real radius. That means the interval of convergence includes all the numbers strictly between 2 and 4, but possibly including the endpoints, possibly not. Or possibly including one endpoint and possibly not including the other. So you have to think about the endpoints. A and D can be ruled out right away. Your interval has to be centered at that number, 3 in this case. What about the other answers? We've got to think about those endpoints one at a time. When x is 2, what does the series become? It becomes, replace x with 2, you get -1 to the n over n. This is the alternating harmonic series. It's conditionally convergent, like we saw in that other problem so long ago. It does converge, though, by the alternating series test. When you plug in the other endpoint, 4, you get the harmonic series itself. Alternating harmonic series converges, the harmonic series itself diverges. Therefore, the series, the power series, converges at 2, but not at 4. B is the answer. You've got to check those endpoints. We're halfway done. Wow. In my time, this has taken way longer than I expected because I kept making mistakes on problem number 6. The height of the rectangle with the largest area that can be described under this graph is what? Pretending this rectangle is the largest area, we're after what that height is. Now, actually, I've drawn it so that that's not the maximum height. So maybe that's a bit misleading. But keep that in mind, is that what you're after is a height here. Height of a rectangle with maximum area. So what do we need to do? This, we should probably call this value just an arbitrary x, which would mean this number here, since this rectangle is centered at 0, would be -x. And that would mean the length of the base is 2x. That seems relevant. And that allows us to find the area of the rectangle as a function of x, base times height. 2x times this function. In general, at a general value of x, that's what this height is actually. At a general value of x, the question mark was, what is the height where the area is maximized? So this is the function here that we need to now maximize. But the maximum value is not the answer to the question, and the x value where it's maximized is not the answer to the question, but the corresponding height. Plug back into the original function. That will be the answer to the question. So to differentiate this, I can use the quotient rule, which I always remember by the way, as low d high minus high d low over the square of what's below. We've got a fraction here. We've got a high function and a low function. Low d high, the derivative of the top, d means derivative, low d high, minus high, 2x. D low, the derivative of the low function is 6x over the square of what's below, 1 plus 3x squared quantity squared. Simplify this, you're going to get 2 plus 6x squared minus 12x squared over 1 plus 3x squared is 2 minus 6x squared divided by 1 plus 3x squared. What value of x makes that 0? What's my critical point? Set this equal to 0 and solve for x. The top will have to be 0, so 2 will have to equal 6x squared. X squared will be 1/3. So x is plus or minus 1 over root 3. Although in my drawing I'm taking x to be positive, so I just have to consider the positive 1 over root 3. That's not the answer. B is, that root 3 over 3 is the same number as plus 1 over root 3, but it's not the answer. You got to plug that number into the original function here. To get 1 over 1 plus 3 times 1 over root 3 squared is 1/3. 3 times 1/3 is 1/3 is 1. 1 over 1 plus 1 is 1/2. The answer is 1/2. So whatever base gives you a height of 1/2, that would be the rectangle that has the biggest area that's inscribed under this graph. Kind of a neat little problem. All right, integral of a rational function here. Partial fractions, right? Take this thing and write it as some constant a over x minus 1 plus another constant b over x plus 5. Try to do that. Solve for a and b where that's equal for all x, where it's defined, and then integrate the function by integrating these two individually and adding the answers. And perhaps simplifying with properties of logarithms in this case. So we want to solve for a and b. We want these things to be equal for all x, where this is defined at least. Multiply both sides by that common denominator there, x minus 1 times x plus 5. What you get when you do that, you get complete cancellation on the left, and it's just a 12. On the right, you get partial cancellation, like this. Now, technically speaking, you might say it's more valid to expand this out as a plus b in parentheses times x plus 5a minus b in parentheses, set it equal to 12. That will give you a system of equations that have to be true. A plus b would have to be 0 because there's no x term there. 5a minus b would have to equal 12, and you'd solve that system of linear equations. However, there's a trick you can use to solve for a and b more quickly. If you plug in x equals 1, for example, that'll allow you to solve for a more quickly because the b term will go away. 6a is the right-hand side, so a is 12 divided by 6, a is 2. Now you might scratch your head and wonder if this is valid, because this original function is undefined when x is 1. It does give you the right answer, and you can double check that. Okay, so for sake of time, it is probably the best thing to do, at least if your partial fraction example is fairly simple. There's plenty of really complicated partial fractions examples that can be made where maybe solving a linear system found by setting the coefficients of like terms equal to each other might be better. Solve for b in the same kind of way. So negative 6b. b is going to be negative 2. So now the integral is going to be the integral of 2 over x minus 1 minus 2 over x plus 5. Do each of those integrals individually and subtract the answers. 2 natural log of the absolute value of x minus 1. Oops. 2 natural log of the absolute value of x minus 1 minus 2 natural log of the absolute value of x plus 5 plus c. Then you can, with these two terms, you can factor out a 2. And you also can use the fact that the log, the difference of two logs is the log of their quotient. 2 natural log of the absolute value of this thing divided by that thing, x minus 1 divided by x plus 5, and don't forget your plus c. And so the answer is choice D. Okay? All right, on to 18. What does that infinite series equal? By the way, this is something I always emphasize to my students. When you are talking about infinite series and what do they sum to, you're not literally doing a sum. Nobody can literally add up infinitely many things. It's a limiting process. Okay, I'll just leave it at that. It involves a limit to precisely define what this symbol means. It might be helpful to go ahead and write the first few terms here. When k is 0, you get 1/3 to the 0 power, which is just 1. When k is 1, you get 1/3 squared, which is 1/9. When k is 2, you get 1/3 to the 4th power, which is 1 over 81. You could stop there. When k is 3, you get 1/3 to the 6th power, 1 over 729, etc. This is geometric. And hopefully you could recognize that even by looking at the sum. The first term, which is commonly called A, is the first term, leading term. What is the common ratio? Take any one of these numbers except the first and divide by the preceding one. You always get 1/9. Conversely, multiply any term by 1/9 to get the next term. R is 1/9, which does have an absolute value less than 1. This series does converge. And the answer is A over 1 minus R. So 1 over 1 minus 1/9. So 1 over 8/9, which is 9/8. That's the answer, choice B. Okay? I think writing it out has the benefit of avoiding the mistake of thinking maybe the common ratio is 1/3. This is the same as 1/3 squared to the k. In other words, 1/9 to the k. The common ratio is 1/9, not 1/3. A number of these last group of problems are shorter than the first group. I really gave myself long, difficult problems for the first 15 problems or so. The last 15 do go quicker. What is this function of the Taylor series for about x equals 0? This power series. Rather than trying to find the Taylor series for each one of these individually, it's better to have some things memorized. Okay? The Taylor series for e to the x, for example, I'm going to go ahead and write these out. It's 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and then you keep following that pattern. That's converges for all x. The radius of convergence is infinity, and these are equal for all x as well. Cosine of x turns out to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, etc. That also converges for all x. The radius of convergence is infinity and equals cosine of x for all x, it turns out. Once you, again, define what infinite summation means, which is not literally adding infinitely many things, but it's a limiting process. Notice all of those terms are even powers. Cosine is an even function. You have a similar pattern with the sine function, except it's with all the odd powers. Sine is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, etc. What about e to the negative x? Well, it's the same as the series for e to the x, except replace all the x's with negative x's. So the odd powers end up having minus signs. And that helps you quickly see that A is the answer. If you look at the series written up there at the top, you could expand it out to see it equals this. You could also notice right away that the x powers are n, not 2n, and not 2n plus 1. So that rules out the sine and cosine right away, and the alternating sign. It's A for the answer. You wouldn't have to write out all these to solve it. This problem can be done a couple different ways. And though each way you can do it, each of these two ways, produces actually a different looking answer. So does that mean there's not a unique answer? Well, the answer to that is it depends on what you mean by unique. Perhaps the most common way people would do this would be to do a substitution. Let me put it up here. U equals x plus 3. Then du is going to be dx. So you have a u in the bottom, and the dx would be replaced by du. What about the x on the top? Well, that can be replaced by u minus 3. So this integral can be written as the integral of u minus 3 over u du, which is easier to do because it's the same as the integral of 1 minus 3 over u du, which gives you u minus 3 natural log of the absolute value of u plus c. Don't stop there, go back to x. U equals x plus 3. This is x plus 3 minus 3 natural log of the absolute value of x plus 3 plus c. Huh. That answer is nowhere to be found in parts A, B, C, and D. Combine the c with the 3 with the c. That's the way to finish. It gives you an equivalent answer. X minus 3 natural log of the absolute value of x plus 3 plus c. 3 is a constant. You can combine it with the other c, since c is arbitrary. And so that tells you the answer is B. A second way this can be done, which actually gives you the right answer right away, is to rewrite this fraction using long division, quotients and remainders. How so? Notice the degree of the top and the bottom are the same, and in general you've got to, if the powers were higher, cubes for example, you'd really have to do the long division instead of a substitution perhaps to solve the problem. The numerator goes underneath the long division symbol, the denominator goes to the left here. How do you do this? You ask yourself, what do I multiply the highest power here by to get the highest power here? I need to multiply x by 1 to get x, so put a 1 up there. Now take that thing and multiply it times each term here. Put the answer down here and subtract. The x's cancel. 0 minus 3 is negative 3. Once you get to a point right here where this thing is a polynomial with a degree less than the degree of what we're dividing by, which it is, it's got degree 0, we're dividing by something at degree 1, then that's the remainder in the division, and this is the quotient. Quotient remainder. And what this means is the integrand function can be written as the quotient 1 plus the remainder negative 3 divided by the original thing we were dividing by, x plus 3. Integrating that as is now gives you x minus 3 natural log of the absolute value of x plus 3 plus c. Choice B right away. Okay? But either method is technically valid. This one's not as hard as it looks. Here we go again, second FTC problem. They're almost always easier than they look. Function capital F defined with a variable in the upper limit of integration. Maybe right away we want to use the second FTC. I don't actually have to do the integral before differentiating this function. I'm after its tangent line, so I'm going to need to know its derivative, as you would expect in a problem like this. I don't need to integrate first before differentiating. I can just, in a sense, cancel the integral sign when I differentiate. I get this integrand function with a t replaced by x. I want the variable there to match the variables here and here. They need to be the same. T is just a dummy variable. I need the equation of the tangent line, so I need this derivative evaluated at pi over 2. I also need the function value at pi over 2. Although the function value at pi over 2 is easy. F of pi over 2 is going to be the integral from pi over 2 to pi over 2 of the integrand function for t sine t over 3. That's like finding the area of a line. The answer is 0. So this graph goes through pi over 2 comma 0. What about the slope of the graph at pi over 2? Plug in pi over 2 here. Pi over 6 is 30 degrees. Sine of pi over 6 is 1/2. The 4's end up canceling. This is pi. So the equation of the tangent line, if I think about point slope form right away, is y minus 0 equals pi times x minus pi over 2. Pi over 2 there. Expand this out, and evidently we need to rearrange it. Y equals pi x minus pi squared over 2. Looks like I need to multiply everything by 2 and also rearrange. 0 would equal 2 pi x minus 2y minus pi squared. That's choice D. (22) can be differentiated at least in a couple of ways. We are going to need to find the derivative of this function because we're afterwards decreasing. You can use the product rule. You also could just multiply this out right at the start. Either way you do it, when you find the derivative, it's going to be beneficial, it turns out, to write it as one fraction. That's not obvious, but that's going to be the case. I'll do it with the product rule. I would encourage you to check it with this form of the function. Product rule is what I'll use. First function is x to the 2/3. Second function is x minus 5. The derivative of the first is 2/3 x to the negative 1/3, and that's how a fraction is going to come involved because of the negative power. That's the derivative of the first times the second, plus the first times the derivative of the second, and the derivative of the second is 1. Common denominator to use is the one that this first term already has, really. It's 3 cube root of x, 3x to the 1/3 in the bottom there. On top, the 2 times x minus 5 will be a 2x minus 10. And then with the second one, I need to get that common denominator, so I need to multiply this thing by 1 in a disguised form. The disguised form would be with the common denominator in the top and the bottom, 3x to the 1/3 divided by 3x to the 1/3. That'll give me 3x over 3x to the 1/3. Combine these now, you get 5x minus 10 divided by 3x to the 1/3. Okay, so what are we after? We're after where the function, original function, is decreasing. So where is this derivative negative? It's probably best to be extra careful here and think about a number line, and think about marking where your critical points, really, where the derivative is 0 or undefined. It's undefined when x is 0, and it's equal to 0 when 5x minus 10 equals 0, which means x equals 2. And now think about the sign, positive or negative, of this fraction in these three different intervals by plugging in numbers, like -1, for example, over here. If I plug in -1 on the top and the bottom, I for sure get a negative on top, and the bottom I get a negative. The cube root of -1 is -1. We're talking the real cube root. So I get really a negative divided by a negative here, which is positive. The function is not decreasing when x is less than 0. When x is between 0 and 2, like when x is 1, I get a negative divided by a positive, which is negative. F is decreasing between 0 and 2. It looks like probably D is the answer, yeah. That's got to be the answer. You may want to double check what happens over here when x is bigger than 2, like 3, I get a positive divided by a positive. Positive divided by a positive, which is positive. Function's increasing over there. Okay? So D is the answer. That's where the derivative is negative. That's where the original function is decreasing. The acceleration of a particle moving along the x-axis at an arbitrary positive time is given by this function there. When t is 1 second, do notice t can't be 0 seconds here. Kind of a weird example, but go with it. The particle is at location x equals 2, that's its position, and moving with a negative velocity. So if you imagine motion along an x-axis back and forth, it's at x equals 2 at this moment in time, and it's moving to the left because the velocity is negative. 1 unit of distance per second. What's its position when t equals e cubed seconds? Actually, let's see. Okay, let's just be careful here. So what do? You need to integrate to find the velocity first, and then integrate again to find the position. And you may need to be extra careful about constants of integration. V of t, you could write as an indefinite integral of a of t, though keep in mind that the plus c would be something specific. C would be something specific based on the initial velocity of being -1 at time 1, if I call that the initial time. That's t to the -2, so when I integrate, I get t to the -1 divided by -1. -1 over t plus c. But now c again is something specific. I know that at time 1, the velocity is -1. And that implies c is 0. But it could have been something different. It could have been something non-zero. By the way, you can also write v of t as a definite integral if you want, plus a constant probably, but it's probably better to do it this way. Less likely to make a mistake. What about the position, x as a function of time? Integrate the velocity. Integrate -1 over t. And again, find an appropriate c. Integral, that's going to be negative natural log of the absolute value of t. T is positive here, so I don't really need the absolute value signs. Now use the initial position of 2 when t is 1 to say, since natural log of 1 is 0, that c is 2 in this second integral. The c is 2. So x as a function of time is 2 minus the natural log of t, and again I don't need absolute value signs here because t is positive. So now when t is e cubed, x of e cubed gives me 2 minus natural log of e cubed. 2 minus 3 is -1, because natural log of e cubed is 3. So -1 is the answer choice D. We're coming into the home stretch here. And I probably should call my wife because I'm taking longer than I thought I was going to be. But I think these last number of problems do go generally pretty quickly. Infinite first quadrant region bounded above by a certain curve is rotated about the x-axis. Here's your exponential decay curve in this problem. Y equals e to the negative 3x. This is rotated about the x-axis, this region here, and it generates what's called a solid of revolution. It generates something that's going to be like an infinite horn. Like that. That goes on forever. What's its volume? You might think initially the volume would have to be infinite since it goes on forever, but no, it could be finite. It's like any kind of improper integral type of thing. The answer could be finite if the corresponding limit exists, and it is in this case. But how do you actually find the volume? Think about slicing again, like that problem with these where the cross-sections were squares. But this time the cross-sections are not going to be squares. The cross-sections perpendicular to the x-axis are going to be circles, or discs would be a better way to say it. There's your typical cross-section. The area function then, a of x, is going to come from the formula pi r squared. Pi times the radius squared. But what's the radius? The radius varies. It depends on what x is. It's smaller as x gets bigger. It's large when x is small. The radius for a given x is this distance right there. This function you could call r of x for this solid of revolution. This is pi times r of x squared, which for this example is pi times e to the negative 6x. And that's the function you integrate to find the answer. And the integral is an improper integral going from 0 to infinity. Okay, I think I'm going to make an exception for the sake of time here and be lazy and not write the limit sign. Are you okay with that? Probably you are. If you integrate this by guessing, you'll get negative pi over 6 e to the negative 6x. And I'll put a 0 and an infinity up there instead of a b, and I will not bother putting the limit as b goes to infinity. It really is a limit going on. I'm not literally plugging in infinity. If I imagine x is infinity, I've got e to the negative infinity power, that's really 0, but it's really a limit again. Maybe I shouldn't be doing this. I'm going to get 0 minus, plug in 0, e to the 0 is 1, you get minus negative pi over 6. The answer does exist as a finite number. It's pi over 6. That is the volume. If the units of length were in, say, meters, the units of the volume would be in cubic meters. Here's a problem where you may not remember the formula for the area bounded by a polar graph. Here's our polar function. To graph this, you don't graph it in the ordinary way. You graph it in what's called a polar coordinate system. And as you let the angle theta vary, or you got a ray emanating from the origin, then the distance r from the origin varies, and it traces out a graph. And r can't be negative here. So that's kind of a tricky case when that happens. And if you plugged in different values of theta here and made the graph, I'm just going to tell you what it would look like. It would look about like this. Kind of a sideways heart. In fact, it's called a cardioid, as theta varies from 0 to 2 pi. And the area is the area of this heart, but in general you want to think of it as an area sort of like swept out by a vector as the vector rotates, as theta varies from 0 to 2 pi. So in general you don't want to think of it as an area under a graph. You want to think of it as an area swept out. But in this case, the area swept out as the arrow keeps going around, including down here, for example, is the entire shape. So the area we're after is the area of that cardioid. How do you find it? Well, the formula is to integrate this function here, call it f of theta. You want to integrate 1/2 times that function squared over the entire interval, in this case from 0 to 2 pi. And this is pretty nice because we don't actually have to do the integral. And we're squaring a square root. The square root goes away. So we're integrating 1/2 times 1 plus cos theta d theta from 0 to 2 pi. But then our heart sinks as we look at the answers and say, hey, none of those is the right answer, it seems like. Take a deep breath. Maybe they're testing something else here. And they are. This thing right here is an even function. Now you might ask, what does an even function mean in polar coordinates? There's some symmetry involved. We could graph it in rectangular coordinates. We could make an ordinary graph of it and interpret this integral as an area under a graph. We could do that. And if you did that, it would confirm that the integral of this function is double the integral of the same function from, well, 0 to pi. Okay, I guess that's not the best explanation because this interval is not centered on 0. It does give the right answer, but the reason is not because it's an even function. It's got symmetry with respect to theta equals pi. The ordinary graph has symmetry with respect to theta equals pi. Oops, and I forgot my 1/2 here too. If you graph the original function in an ordinary kind of way, with this being a theta axis on the horizontal axis, I mean, you have to think about it. It's going to look like this. This is going to be pi right here. This is going to be 2 pi right here. Its maximum value, I'm talking about this function here, is when theta equals 0. It's 1 here. Its minimum value is when theta is pi, and that means I'm actually not graphing it accurately. The theta axis is actually up here. Its minimum value is 0. Right there. Oops, it's pi, but its value is 0. It's 2 pi. The area here and here are the same. Okay, they don't look the same in the picture, but they are the same. It's got symmetry with respect to that vertical line at pi in an ordinary kind of graph. So that justifies this. And then the 2's cancel. And you're left with answer B. Right, so extra tricky, and I was thinking about it wrong at first in terms of even functions. I mean, it's a similar kind of thing, but it's not technically the fact that it's even that you need. Which of the following converge? This is just based on knowledge of facts. That's 100 times a p-series with p equal to 2, which is bigger than 1, it converges. In spite of the fact that 100 is a much bigger number than 1. This one converges. This one is really geometric terms divided by n, they're smaller than geometric terms. Geometric with common ratio 3/4, which would converge, the series would converge. When you divide by n as well, you're going to have terms that are even smaller, still positive, by something called the comparison test. This one would converge. And this one, in spite of the fact that the 100 down there is kind of big, still has terms which do not go to 0. The terms that you're adding here approach 1 over 100, something non-zero as n goes to infinity. And that means the series diverges. The terms converge to 1 over 100, but the series, the summation, diverges. Make sure you keep those concepts distinct. So the answer is 1 and 2 only. Euler's method, which in general could take a lot of work, but this one goes pretty fast. dy dx equals 1 over 2x plus 1. There's your differential equation. Let's call this function f of x. Y of 0 is 0. Find an approximation for y of 1 with Euler's method. Step size 0.5. You do say Euler, by the way, not Euler. Euler's method. The method in general gives you the next value of y sub k plus 1, by taking the previous value of y plus the change in y. And the change in y is found by plugging the point you're at into the function, that's the right-hand side of the differential equation. In this case, it just depends on x, but it could sometimes depend on y. So in general, there could be both an xk and a yk in the argument of this function. In fact, it's much more interesting when it does involve y. But in this case, it just involves x, so we can just put an x in there, times delta x. So I'm not going to explain where this formula comes from, other than just to say it comes from essentially equations of tangent lines. That's where it comes from. Then you may want to make a little table to help you here. We're going to need 2 steps of Euler's method. When k is 0, what is x0? It's 0, right there. What is y0? It's also 0, right there. What is the change in y? Plug in 0 into f, and then multiply by 0.5. F of 0 times 0.5. Plug in 0 here, you get 1. 1 times 0.5 is 0.5. X automatically keeps going up by delta x. That's the same every time. But the change in y doesn't have to stay constant. It happens to be the same as the change in x here. And we get 0 plus 0.5 is 0.5. But it didn't have to be the same as the change in x. One more step. Find f of 0.5 times 0.5. Plug in 0.5 for x there. You get 2 times 0.5 is 1. 1 over 1 plus 1 is 1/2. Get 0.5 times 0.5. Almost made a mistake there. Equals 0.25. That's the change in y. The previous value of y is 0.5, so I add 0.25 to that and get 0.75. And that is the same as 3/4, of course. D is the answer. And that approximates the function at x equals 1, which means this is actually a mistake here, sorry. It's 1.0. Just 3 more problems. For which of the following series does the ratio test fail to give a conclusive answer? Tricky wording. The question is not which of these converge and which diverge. The question is which does the ratio test fail to give a conclusive answer. In the ratio test, you look at the limit as n goes to infinity of the absolute value of an plus 1 divided by the absolute value of an. It's similar to the power series where we were finding the radius of convergence. Not exactly the same. There, when we did this limit, we got, I think, 1/3. and we took the reciprocal of that to get 3 for the radius of convergence. Though I did mention you could think of it in terms of the ratio test if you also thought about the x's in that problem. Here it's a pure ratio test problem. We're wondering, not only does this limit exist, but is it less than 1 or bigger than 1? If it's less than 1, that'll mean the series converges. If it's bigger than 1, it'll mean the series diverges. And in both of those cases, the ratio test is giving a conclusive answer. The only possible way to get an inconclusive answer in simple examples like this is to get a limit equal to 1. Got that? So it's when this limit equals 1 that it gives an inconclusive answer. It gives a conclusive answer when it's either less than 1 or bigger than 1. In the case of the first one, and in all the, well, I guess this one we have to get rid of the negative sign, but I only have positive terms there. There's an plus 1. Divide by an means divide by the reciprocal when you have just n's instead of n plus 1s. And whenever you have factorials like this, they cancel partially. That completely cancels. This partially cancels to leave an n plus 1. This completely cancels. This partially cancels to leave a 10. You're left with the limit as n goes to infinity of 10 over n plus 1, which is 0, which is less than 1. The ratio test does give a conclusive answer that this series converges. It's a little surprising because you've got a numerator, 10 to the n, that's growing so large so fast, but n factorial grows even much larger, much faster than 10 to the n does, fast enough to make this series still converge. But it does give a conclusive answer. That's the more important thing. With this one, if you do the same limit, in this case, you get a limit as n goes to infinity. It would be the negative 1 to the n, and n plus 1 will go away because of the opposite value signs. You get 3n plus 1 over 3n plus 4. And that has a limit that equals 3 over 3, which is 1, which is the inconclusive case. 2 does not give a conclusive answer with the ratio test, though this series does converge by the alternating series test. The ratio test gives no conclusion. The ratio test is actually a pretty weak test because it doesn't apply to as many cases as some other tests do, in a sense. This is an example where it gives no conclusion, though the alternating series test would tell you this series converges. Finally, what about this one? The resulting limit would be, well, let's maybe simplify this first. That's n cubed divided by n to the 1/2. So you're going to get n to the 2.5 power, 5 halves power. This series will not converge. It definitely diverges by the divergence test. However, the ratio test gives no conclusion, and we will see here in a second, because it's going to be n plus 1 to the 5 halves divided by n to the 5 halves. And something to the 5 halves power is a continuous function. I can bring the limit in there. This is a, can't see it so well. N plus 1 over n. As n goes to infinity, that goes to 1. The whole thing goes to 1 to the 5 halves, which is 1. Once again, the ratio test gives no conclusion, even though this series definitely diverges. So the only one that gives a conclusion is 1 only. Okay? How many terms of the converging alternating series that you see there are required to approximate the sum of the series to an error less than or equal to 0.01? The absolute error of an alternating series that satisfies the conditions of the alternating series test think of S as being the sum of the series. Think of Sn as being the nth partial sum as the sum of the first n terms. This absolute error is always less than or equal to the, well, if we're thinking the ANs here as being the terms that are added except exclude the negative sign. If those are the ANs, they're not the terms because of the negative 1 to the n plus 1, but if we exclude that, and if I call those AN, the alternating series test says this is bounded by AN plus 1. Okay, it's something you can look up. These A's are all positive. The series itself is alternating in sign. And so for this problem, that's 1 over n plus 1 quantity squared. And I want that to be less than 0.01. I want that to be true. What values of n make that true? This is the same as 1 over 100. Just solve the inequality for n. You can flip both sides, take the reciprocal. If you do, the inequality changes direction. Then take the square root of both sides. You can think of it as the positive square root. So no absolute value signs are necessary. N is positive. It's an increasing function, so the inequality stays the same direction. Now subtract 1 from both sides. N must be greater than or equal to 9. So that is the answer there. It's possible it could be closer than 0.01 to the true answer when n is smaller than 9. But as far as this theorem goes, to guarantee it, you need 9 or bigger. And that's what you really want is the guarantee from the theorem. Last question. And it's actually a lot easier than it looks. The density in cars per mile along a 30-mile stretch of the New Jersey Turnpike starting at a toll plaza is given by this density function. So cars per mile is the units of that thing, where x is the distance in mile from the toll plaza where you started, and x is between 0 and 30. What's the total number of cars? Now realize this is probably unrealistic, though, at least having an exact formula like this. It might be a reasonable approximation in some circumstances. If you study traffic flow, traffic does tend to flow in sort of like an accordion-like fashion when there's a traffic jam. But it's similar to a problem where you could be given the density of like a thin wire in, say, kilograms per centimeter or grams per centimeter, and you'd integrate the function to find the mass. Here you integrate this function to find the total number of cars. Now in real life that would just give you an approximation, but we are after an exact answer here. So the answer is to integrate that function, integrate the density over this domain from 0 to 30. And the part involving the sign is actually going to integrate to 0. When you find the antiderivative, you'll get 400x. If you want to go ahead and be careful about it, write it as minus 100 over pi cosine of pi x, evaluated from 0 to 30. But when you plug in 30 and when you plug in 0 into this, you'll get cancellation, okay? Because cosine of 30 pi and cosine of 0 are both 1. You get a 1 minus 1 is 0, in spite of the 100 pi up front. 100 over pi times 0 is 0. The only thing that gives you something non-zero is the 400x. And that gives you 400 times 30. And that is 12,000. So 12,000 is the answer. I commend you if you stuck with me through this whole thing. I am really tired. Happy to get it done. And I wish you well on your test and also in staying safe with COVID-19 going around. Thanks for watching.